what if I was to put a 2 pi here? What would it be if I cut that in half? That'd be 1 pi, right? Take marks of pi. What if I cut that in half? Half pi, or pi over 2, right? So what would this one be? 1/2, 1 whole, 1.5, or 3 pi over 2. So those are all the quadrants, right? Pi over 2 is 90 degrees, pi is 180 degrees, 3 pi over 2 is 270, 2 pi is. Okay, what if I was to go backwards? Negative, 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 negative. This isn't a unicircle. This is just an xy axis where I'm putting all of my thetas, on my x-axis. And what's going to go on the y-axis? The values of sine. And more specifically, I'll just do y equals sine of theta. Now, values. Hold on. Values. Values are what sine equals at a certain angle, right? So, help me out. Do you guys remember sine at 0 degrees or at 0 radians? What's the sine value at 0?
0.
Sine is the y, and the y is 0. How big does sine get as we go around the unit circle? Do you remember? No bigger than 1. Because it does the square roots up to 1, right? Remember our table? Up to 1, and then it goes back down to 0. Wait, can it also go negative though? So it can go up to 1, it can go down to -1. Okay, but where is it at pi over 2? We'll go 0. Oh, that's at 1, right? And then at pi it's 0 again. At 3 pi over 2 it's -1, and at 2 pi it's back to 0. What angles are missing from in here? In the unit circle at least. The 30s, 60s, and also the, what are the in-betweens? The 45s. Wouldn't those fall right here in the first quadrant between 0 and pi over 2? We'd have like our little pi over 6, pi over 4, pi over 3. We're not going to go crazy and mark all those. But if I was to do pi over 6, sine is 1/2, remember? And then it goes to square root of 2 over 2. Then it goes to square root of 3 over 2, which is almost 1. If you guys notice, this isn't like a straight connection. It's actually more of a rounded concave down connection. And if we were to keep on doing our 60s and 45s and 30s, it'd be rounded again, and then it would be rounded again, and then it would be rounded again, and guess what? It keeps cycling. If I was to go the other way, going down 90, going backwards 180, it actually does the exact same cycle. Again, sine is what we call a periodic function, meaning it repeats every, for this example at least, every 2 pi. Every 2 pi it cycles. We actually also call sine and cosine waves. If you were to drop a pebble in like a still, calm body of water, drop a pebble in, what happens?
Ripples.
Yeah, there are ripples, there are waves, right? You can get your calculator out. There are ripples or there are waves, and guess mathematically what we could model those waves with? Sine and cosine. However, look here and just imagine, it keeps on repeating and repeating and repeating and repeating, right? Why is that not going to perfectly model the pebble in the water and then the ripples that...
Because it stops.
Right, the ripples eventually, don't they decrease in there? Do you guys know what the height of a wave is called?
Crest.
Not crest, not magnitude.
Crest is the bottom, right?
Think sound waves. Does that help?
No.
Because sound travels in waves too. Light does also. But if you're trying to make something louder,
Amplitude.
amplitude. If you're trying to amplify, if you're trying to amp it up, right? Sound waves. Sound amps. Does that help a little bit? Okay. A sine curve by itself is going to keep on, this is like an ideal situation, a sine curve by itself is just going to keep on cycling. If you can imagine, it's like in a vacuum or something. There's no other force acting on it that makes eventually the water to go ahead and calm or to still. A normal sine curve is going to keep on going forever. Now there are other mathematical things that we can do in order to amp it up or to de-amplify it or to go ahead and let it,
I said a bunch of things.
in a sense, kind of go to rest. But for right now, we're just looking at the ideal. As soon as we go into all the craziness of an actual real life example where it does start at a certain height and then get smaller, suddenly the math gets harder. So we have to learn the basics first. Now that's a sine curve. If you guys notice, what happens with the wave here? Does it start being disturbed or does it start from rest?
Rest.
Why? Because sine always starts in the middle. Sine always starts, in a sense, you could say, at rest. Then suddenly the wave begins. Now, cosine's a little bit different. At 0, sine is 0, but at 0, what is cosine?
1.
So let's go ahead and make another graph. If you think about in a unit circle, what sine can equal and what cosine can equal, maybe you'll realize that these are going to be super similar. Because they're both going to repeat every 2 pi. Those are not evenly spaced. Hold on. They're both going to repeat every 2 pi. So they're going to have the exact same tick marks. I'm not going to label all of them because we did up above. Cosine, just like sine, also goes up 1 and goes down 1 in the sense of going -1 and +1. In the sense of going -1 and +1. But the difference is sine starts at 0. What's the first x value at 0? What's the cosine value? 1. Cosine starts being displaced. Cosine starts being displaced. In the sense of sine starts from rest, and cosine already starts at its maximum value. Now, if I was to go ahead and keep going, cosine starts at 1. At 90 degrees or at pi over 2 it's 0. Then it's -1, back to 0, back to +1 at 2 pi. It also cycles. And if I was to go through and do the 30s and the 45s and the 60s, you would realize, where's our 60? About here, here, here. You would realize that cosine is also curved. The nice thing is we already did our sine curve, so we already kind of figured out that this is a wave and so it's going to be curved as it connects. It's not going to connect in straight lines. We can go back and do the main values again. These are actually called the principal values. There are lots of values in between, infinitely many if you guys remember. How in between every tick mark, oops, that should have connected. In between every tick mark there are infinitely many values, but the main ones are the ones that mark our quadrants. Our 90, 180, 270, 360, or our in radians, pi over 2 pi, 3 pi over 2, and 2 pi. If we can get those main points, they're called principal points, we can connect it with a wave. Now, remember I said these were both of our most basic graphs for sine and cosine. Technically, we should probably call them, instead of basic, we should call them parent functions. Uh-oh. When did we talk about parent functions this year?
Translation.
Maybe 1 or 2 chapters?
Yeah, it was like 2 chapters ago-ish, chapter 1-ish. Parent function of a quadratic, parent function of a x cubed, parent function of an absolute value. Then we talked about parent functions of e to the x and ln of x. We started introducing more. Now we're introducing sine and cosine, parent functions. Yes, it's important to know the shape of the basic curve, and then we can use that to say, okay, what if? What if you want to amp it up, meaning the amplitude of the wave gets higher? That's going to be a transformation, specifically a dilation, a vertical dilation that stretches it. What if you want to quiet it, or what if you want to calm, like the wave in the water, etc., mathematically speaking? Well, then we need to go ahead and have a vertical dilation that's making it shrink instead of compress. Instead of stretch. Shrink and compress is the same thing. So we're getting into transformations. These are the parent graphs. These are the basic ones. And what's the shape? You guys already figured out that they're waves, but to be all particular, we call them sinusoidal curves. Sinusoidal, how come?
Legally sinusoidal founder.
Yeah, okay.
Kind of, they're curves that are being expressed or modeled by
Sinusoidal curves.
sines and cosines, and if you think about it, cosine, that's the co-function of sine. It kind of all comes back to sine. That's why it's called sinusoidal. Just think sine and cosine, what do they have in common? Sine.
Why can't they just call sine curves?
That's no fun, sinusoidal sounds so much more fun.
Sinusoidal does
It's like sinuses, but not, wait, are sinuses?
Sounds like.
Come on, say it at least 2 times, sinusoidal.
Sinusoidal.
It's not
It sounds like you're from the Bronx or something. Sinusoidal.
Sinusoidal.
Alright, here we go.
Double suit should say, so it's like Pokemon.
A Pokemon? I was thinking it sounded like you're from New York, but okay, fine. I'm gonna say Pokemon. Those of you who aren't smiling, you didn't say it, did you? Alright, here we go. Key points. Principal values, these are the ones I was talking about a second ago. Sines and cosines, since they're wavy, curvy, sinusoidal curvy, whatever, they can be kind of complicated to draw. So I'm going to try and break it down. I'm going to try and break it down to, first of all, making sure that we understand the key points, where to put them, how to find them. Talk about, all right, what if that's all we cared about were the key points? And then we'll say, maybe we should break it down a little bit more. So unlike in chapter 1 when we talked about translations and dilations and reflections, we're still going to talk about them, but we're going to try and kind of rename them because curves are kind of important. Waves are important. If light travels in them, sound travels in them, motion like water travels in them. Pendulum swing in waves, that might be kind of weird, but how far away a pendulum is from its resting point actually also, if we were to model it on an XY axis, would also be a wave. Springs bounce in waves, if you were to model them linearly. So it's a pretty important thing, so we're going to try and break it down and kind of name each of these different pieces. Don't worry, I'm not changing. The key points are intercepts with the sinusoidal axis. Ooh, who's that? Maximums, minimums, if you guys think about waves, they have a high point and they have a low point, but they also go through a middle, which we would call the resting, or the at-rest height or point. And before I even start talking about transformations, the most important thing to get down right now are the key points. I'm going to go ahead and quickly just show the parent function again for sine, a non-transformed sine, and cosine, a non-transformed cosine. And remember, these waves can get shifted to the right, to the left, up, down, stretched, compressed. So instead of putting them in an XY axis, let me just show you from the beginning of a sine curve, one cycle of sine starts in the middle, goes to the top, comes back to the middle, goes to the bottom, and comes back to the middle. So key points. One cycle of sine, key point, there's the first starting point, there's a maximum, there's another intercept, there's the minimum, and there's another intercept is what we would call it. That's a normal sine curve. Cosine. Cosine starts at the top, then goes to the middle, then to the bottom, then back to the middle, then back to the top. Very similar. When you show lots of cycles, they kind of look almost the same. But cosine starts displaced. But if you notice, cosine still has 5 important points. It just starts with the maximum and then the center, minimum, center, maximum. If it's helpful, if the unit circle doesn't naturally pop into your mind, like cosine of 0 is 1, it starts up. Sine of 0 is 0, it starts in the middle. If that doesn't help, you could also think sine starts in the center. I know it starts with a C, but come on, for the sound, right? Sine starts in the center. cosine doesn't. Sine starts in the center. Okay. So let's take our sine curve. We see him right here. Let's look at a transformed, but you guys help me out, just with your knowledge of transformations of graphs. If there's a 2 being multiplied on the outside, so that first of all, a translation, a dilation, or a reflection.
Translation, no.
Dilation.
Dilation, I don't know.
Dilation, it's a stretching, compressing one, right? And if it's on the outside times 2, what do you think? Is that a stretch or is that a compress?
Stretch.
Good.
Kick up.
Only on the inside is stuff backwards than we think. So we know right now there's going to be a vertical stretch by a factor of 2. Do you guys remember what coordinates change when there's a vertical stretch? Did the x's change or the y's? The y's. So wait, is it going to shift right, left at all? Is it going to shift up, down at all? So we're going to take the sine curve that we just saw and say, hey, it's still going to have 2 pi, right? It's only stretching up, down. The x's aren't changing at all. Negative 2 pi, negative pi, negative pi over 2, negative 3 pi over 2. Ooh, that's not even. Sure. The x's don't change at all. But what is going to change? Okay, so look at your parent function. How high, how low did that one go? Yeah, it went up 1 and then went. Look at your y-axis in the parent function on the page before. It went up 1, but it also went
Down.
down 1. Okay, so if it's going to be vertically stretched by 2, then the only thing that changes is up
2.
2 and down 2. Now technically, isn't that going to change the heights of all the points? But what if we just stick to, bless you, what if we just stick to the 5 key points? I wonder if we could get the whole graph. You ready? What if we stick to the 5 key points? First of all, let's go ahead and have it go up 2 and down 2. But the key points, all right, sine starts in the center, right? Okay, then what does it do? It goes to the top, right? Well, to the top is now going to be 2 instead of 1. Then it comes back to the center. Then it's going to go to the, look at it, right? Top, nope, center, top, center, bottom, which is now at negative 2, then back to the center. I just grabbed 5 points, and do you think I'm ready to connect? Yeah, do you guys see the wave? If that's the top, if that's the bottom, there we go, it's just a little bit stretched. Way better than changing the infinitely many points in between. We never have done that with transformations. We pick a few key points, but with sine and cosine, there's 5 of them. But don't they have a pattern? Center, top, center, bottom, center? Or top, center, bottom, center, top? And then how do we go backwards? Well, guys, where am I going as I come back if it's going to cycle? Down, good. Keep going. Center, keep going. Top, keep going. Got it. See? And how do we say it keeps on going forever? Put our little arrows and say, fine, we're done. 2 cycles are usually more than enough. However, what was the only thing that changed in this one? Yeah, there was just a times 2, but you guys know with transformations, can there be more than one that happen? And it was kind of hard just with one. Like, hopefully it's not crazy. You're like, oh, I see it. It's the same thing, but nothing changed horizontally. Sweet, I just picked to go. There is one other key point up here I want you guys to start. In this example, nothing changed horizontally. Oh, on the interval. We went a little bit more than that. Here. Oops, we did negative 2 pi to 2 pi. We could have sketched for longer, I just wasn't paying attention to the interval. If we had to go to 4 pi, we just have to go another cycle over there, but I don't have room. But nothing changed horizontally. The problem is sometimes things can change horizontally. So if there is a horizontal change, which could be dilation or translation, then we're going to have to pay special close attention to how often each of these 5 points occur. The nice thing is this time, nothing changed. So we knew 0 to 2 pi every quarter of 2 pi, which would be our normal tick marks of pi over 2, pi, 3 pi over 2, 2 pi. But the problem is it's not always that easy. So we have to remember, we can always find the entire period across, cut it in half, and then do quarter cycles to get the other 2 points. The entire period across, but cut it in half, quarter cycles to measure it off. We'll talk more about that as horizontal changes happen, but for right now. I know. But it's a lot better to talk about all these transformations and try to simplify them than just to start going on the crazy hard ones right away, I promise. There are 2 different ways that you might see or be given a sinusoid. Here's usually what you're given. But this is what we want.
Looks like proofs.
Yeah, kind of, but it's not that complicated, because really, if you guys look at it, what's the one difference, what's the one step you might have to do to get it to the nice form that we're gonna talk about? You see the one place it changes? This one leaves the b in, it's right next to the x, and this one says, no, factor the b out, okay? So how do you get from what you have usually to what you want? You want to factor out the b. But then, once you do factor out the b, and sometimes they give it to you in the nice way, sometimes they do. Kind of rarely, but sometimes. Once you have it in this form, well, then we're ready to go. Well, I guess we're not ready to go quite yet, but we will be ready to go. We just need to learn some clues first. So I'm going to write the old-fashioned way of thinking about it off here to the side. If there was a plus on the outside of a sine or cosine, we would call that a vertical shift, right? That's the old way of talking about it. A, if there was a number multiplied, we would, on the outside, we would call it a vertical dilation, yeah, which could be stretch or compress, which is why I don't like to use those when I'm generalizing. B, if there's a number being multiplied by the horizontal, or sorry, on the inside, that would be a horizontal dilation, just being multiplied. Technically, if you remember, on the inside, it's messy. It'd be times 1 over b. We'll get back to that. And then if you're adding or subtracting from the x, that would be a horizontal shift. But remember, backwards of what you think, which is why there's a minus instead of a plus. But here are the new ways of explaining it. D is going to be the placement of what we're going to call, I think of my color coding, what we're going to call our sinusoidal axis. Sinusoidal, if I can spell it. Now, as you can tell, that would be really annoying to write every time, so we're going to say our SA at y equals d. And if you think about it, an axis, it's kind of hard to totally connect this idea for you, but if we were to, let's say you're riding a bike and you run over a fly, and the poor little fly gets squished to the bike tire, okay? Then as you keep going, what's happening to the poor little fly? You're just going around and around and around and around. Now, if we were to go ahead and try to map that mathematically, you're like, well, that's weird. How would we show a circle going around and around and around on a graph? We would show it actually using a sine curve. The fly would start, we would say, it's not the center, it'd actually be like a negative cosine because it would start at the bottom. It would start at the bottom and then it would go ahead and go to the top as high as it can go and then it comes back down and as low as it can go and it's stuck in that little rotation of the bicycle wheel. But think about, where would the axis be? The axis of a wheel is where? Axle, come on guys.
Middle.
In the middle, right? Okay, so sinusoidal axis is actually the middle of the graph. which, and the ones that we've seen was the x-axis, but if that gets shifted, that middle might be somewhere else. A, this one's a little bit easier, amplitude. How high or how low your sinusoidal curve will go. Amplitude, how high or how low. We could say half the distance from top to bottom. Because when you're measuring a wave and you're measuring the amplitude, you're measuring from the middle. So you're going to have a certain amplitude up and a certain amplitude down. Put the two together, it's going to be half that distance. B, okay. B is going to be used to find period. And how is it going to be used? There's a little formula for period. Period is equal to the normal period, 2 pi, but times 1 over b. If you guys remember, horizontal dilations, it was always different than what we thought. Instead of multiplying by b, it's going to be 1 over b. It's the reciprocal. And then c over b, there's a minus in the formula. That's going to be our phase shift. And what that helps us with is that we can find our initial or our starting point. Because we can't graph it, we can't figure out where to start. And each of these clues are going to help us in order to being able to graph the nastiest sinusoids they could possibly give us. Maybe we could do some of the easier ones like the page before without really thinking about much of any of this and only thinking the old-fashioned way. But as soon, you guys look at these formulas, right? Look, they're disgusting, they're messy, they look hard. But if we can break it down to each of these pieces, in each of these pieces, then we'll be all right. Now, we're not going to go too much further because obviously we're almost out of time. We're going to talk through each of these clues tomorrow in a little more detail and make sure we're okay. But here's where we're trying to get. We're trying to get to the point where we can figure out where the middle of the graph is, which is going to be the sinusoidal axis, which could be many different places. We're going to try to figure out from our amplitude how high and how low our graph is going to go. And if we can go ahead and get a starting point, we'll say it's a sine. Then we can measure our center, top, center, bottom, center, and we can connect and make our wave without having to necessarily think all crazily about all the different transformations. Kiddos, before I let you go, when have you seen something like this before? Chemistry, really?
First grade.
I was thinking a long, long time ago.
Oh, no, she's actually.
When you guys first learned to,
Right.
we're gonna learn how to do sinusoids tomorrow. Bye, cool kids, get out of here, I'll see you later. No homework due tomorrow. Homework tomorrow for math. Do any other homework tonight if you can. Bye, guys. Maddie, were you able to finish?
Yeah.
Okay.
Oh, yeah.
The problem was we didn't end. It wasn't necessarily that.
And then like.
You have to treat it as a square root, you have to square it, and so you forgot to square it.
So much square the other side, you can draw 3 or
Oh, sorry, I just marked the 3 out, but you need to be
9, and then you go from.
Then you go,
Okay.
the other way to do it, you write down the number first, multiply them over and then done.
And then, okay, that makes sense.
Does that make sense?
You're here for 7th period, right?
Yeah.
Okay.
Could that work better for you?
Probably.
Okay.
I might be able to.
Alright, see what you can do, thanks Jacob.
Uh-huh.